Hi there, students. Welcome to Geometry with Mrs. Brunk. Thanks for joining me for lesson 16.2 today, which is entitled Arc Length and Radian Measure. And our essential question is, how do you find the length of an arc? So it's a pretty basic question. How do you find the length of an arc? So when you think of an arc, you probably kind of imagine something that's curved, something that's open, it's not like closed like a circle, right? And that's exactly what an arc is. So an arc of a circle is an unbroken part. So it's an unbroken part of a circle that is consisting of 2 points called the end points and all the points on the circle between them. So the definition that we use here is that an arc is a part of a circle. And when we talk about the length of an arc, it's understood to be the distance along a circular arc measured in linear units, such as feet or centimeters. And you can use proportional reasoning to find arc length. So the kind of question we're going to want to be able to answer here is something like, let's say we wanted to know the length of arc AB. So here's arc AB, right? AB along the circle. Now in the last lesson we learned about arc measure. And arc measure was a type of measurement that showed the number of degrees that you turn through on a circle from one point on the edge to the other. And we actually said that it was associated with the central angle. So like the central angle here would be, let's say there was a letter here in the center. Let's say we called it O. Then we'd say the measure of angle AOB is equal to the same thing as the measure of arc AB. Okay, those are the same, and in this case they were both 60 degrees. But what about if instead we wanted to know the linear measurement, or know the actual distance you'd have to travel from A to B? Well, in the last lesson, we talked about the distance we would travel if we went all the way around. So if we started at B and ended back at B, we called that circumference, right? And so it makes sense to think that arc AB is a fraction of the circumference. It's a part of that whole distance around. And in fact, that actually is the formula for arc length. And so we're going to go ahead and find the measure of arc AB by just seeing what fraction of the circle it actually does cover as far as the boundary of it. So really what we're trying to figure out, in fact, is what is the whole circumference of this circle first, and then we'll figure out what fraction it is. So let's go ahead and first find the circumference of the circle. We learned this in the last lesson. We learned the formula circumference equals 2 times pi times r. So the circumference would be 2 times pi, and then the radius of the circle is 9, right? So times 9, which exactly would be 2 times 9, which is 18, and then times pi, or approximately 5486, so about 56.55 centimeters to go all the way around. Of course, traveling along the arc from A to B, we're not going all the way around. We're only going a part. But what part, like what fraction is it of that whole circle? So the entire circle is 360 degrees. We know that. Any circle is 360 degrees. But the arc's measure is only 60 degrees of that, which means that arc's length is actually 60 of 360, or 1/6 of the entire circumference. Okay, because that 60 degrees is actually 1/6 of the measure of the whole circle. So the arc is 1/6 of the measure of the circumference. So the arc length of AB would be 1/6 times that circumference that we already found, which I guess we could leave it as 18 pi and then approximate it later, or just say 1/6 of 56.55. So if I left it as 18 pi, which is like the exact circumference. Then 1/6 times 18 is 3, so that would be 3 pi, or approximately 9.424, so about 9.42 centimeters. So that's how far it is actually to walk from A to B, is a sixth of the 56.55 centimeters, or 9.42 centimeters. Again, I don't see anywhere in here where they ask us where to round to, so I went to 2 decimal places, but just kind of watch. It doesn't say where to round to specifically that I can see. So the arc length of AB is 3 pi, or approximately 9.42 centimeters. So 3 pi centimeters, or approximately 9.42 centimeters. So essentially what we did is we took 60 degrees of the full circle's 360 degrees, and that's how we found our fraction. And then we multiplied it by the circumference, which was 2 times pi times 9. Times 9, right? Which was the radius. But if we wanted to generalize this for just any circle and any arc, which is what we were trying to find was the measure of an arc, right? So if we were calling this arc measure, arc length, not arc measure. Arc measure was in a degree, but arc length, the actual arc length of the arc, we could generalize this by saying, well, we don't know exactly what the measure of the particular arc might be, but let's say we call that m degrees, okay? And we may not know what the specific radius of that circle is, so maybe we'd just call that r. And now all of a sudden we have a formula that we can use for any arc on any circle. As long as we know its radius and we know the measure of the arc in degrees, we can always find the length of the arc. And that's exactly what this formula says right here. It says that they call that S, arc length, they call S. Not sure why, where the S comes from, but anyway, they use that variable to represent arc length, and it's m divided by 360 degrees times 2 pi r. So I'm going to write that a little bit bigger, m degrees over 360 degrees times 2 pi r. Now, of course, if they give you the diameter instead, then you could do pi d, because we learned that those are interchangeable circumference formulas. So my arc length S is equal to this. So now we're going to take a look at a few examples where we're going to apply that. So our first example has to do with a clock. So it says on a clock face, the minute hand of a clock is 10 inches long. So the minute hand, it stretches from the center to basically the outside. So that's like the radius of this circle. And again, it's 10 inches. To the nearest tenth of an inch, which means we're going to be rounding to 1 decimal place. How far does the tip of the minute hand travel as the time progresses from 12 o'clock to 12:15? So it's starting here at 12 o'clock, and then when it gets down here to 12:15, it's going to be right here at the 3, right? So that's what we want to know, is how far did it travel along that arc? Well, first of all, we need to know the measure of that arc in degrees. And I can tell that this is 90 degrees, right? Because I just went 15 minutes, which is a quarter of an hour, and a quarter of 360 degrees is 90 degrees. So that's a right angle right there. So that's my M. My M represents 90 degrees of the full circle, which is 360 degrees. And now we know that the radius is 10 inches. And we can very easily calculate to the nearest tenth the arc length. So first of all, 90 divided by 360, well, that's 0.25, and then times 2 times pi, and then times 10. And that's approximately 15.707, so it's approximately 15.7 inches is how far you'd have to travel to go from straight up 12 o'clock to 12:15. So here's a related question. So this time it says the minute hand of a clock is 6 inches long. So that means my radius is 6 inches, right? To the nearest tenth of an inch. Again, I want to see what they want me to round to, so tenth of an inch. How far does the tip of the minute hand travel as the time progresses from 12 o'clock to 12:30? Okay, if we look at this clock, instead of being going to 12:15, we're going to go all the way down to 12:30. So now that's halfway around that circle, right? We want to know that semicircle, so it's 180 degrees. So it's half of the circumference is basically what we're going to be finding. But this time the radius is only 6 inches, so that's 180 divided by 360, which is really a half, right? Or half an hour, times 2 times pi, and then times that new radius, which is 6. So that's going to be about 18.849, so that's about 18.8 inches is how far you have to travel to go from 12 o'clock to 12:30. Okay, so we've done a couple together. This is your chance to try your hand at it. So we're going to designate this one as a you try question or your turn. This is your turn or your you try question. And I want you to pause the video, give this one a try, and then tune back in to check to see how you did. So pause the video now. All right, so thanks for giving that one a try. I got 37.7 inches. And the first thing I needed to do was figure out this angle. Well, because I'm going from 12 to 12:45, there's a couple ways you could think about that angle. You could think about it, well, from 12 to 12:30 we saw was 180 degrees, and you'd go another quarter of an hour or another 90 degrees. So 180 plus 90 is 270, or you could think about it instead as that there's 15 minutes or a quarter hour left to go. So that's 3/4 or 360 minus 90 degrees, which is 270. So that 270 degrees of the full 360 is basically saying we want 3/4 of the circumference, and that's 37.7 inches. So the next thing we're going to look at is arc lengths in concentric circles. So concentric means same center. So circles that were concentric would have the same center, but might be bigger or smaller than another circle with that exact same center. So consider a set of concentric circles with center O and radius 1, 2, and 3. So kind of like a dartboard. And so on. The central angle shown in the figure is a right angle, and it cuts off arcs at that measure 90 degrees. So in other words, every one of these arcs is the same measure in terms of arc measure, but certainly they would not be the same length, because clearly the ones out further would be much longer than the ones in closer to the center. So arc length, the size of the circle, matters. Arc measure, it doesn't, because we're talking about how many degrees we turn through. So then that's the big difference between length. It's a linear measurement, so the bigger the circle is, the longer that length is, but the measures of a circle, still the degrees still add up to 360. That's the max, right? So the angles aren't going to change based on the size of the circle. So we're going to explore this a little further. So it says for each value of the radius are listed in the table below. Find the corresponding arc length. So they said like one of the circle, like the small circle is radius 1, that's right here, right? Then the next one was 2, and so on. So for that smallest circle, if the radius is 1, the arc length would be 1/2 pi. Where that comes from is this, just to kind of give you an idea. It's saying that's the 90 degrees divided by 360 degrees, but then times 2, then times pi, and then times 1. So why it's 1/2 pi? It's basically, they simplified it down to multiplying the numbers besides pi. So that would be 90 degrees over 360 times 2, which turns out to be 0.5 or 1/2. And so it's 1/2 pi or 0.5 pi. So then if we wanted to get the next one, so we change this radius. So the angle is going to stay the same, but now the radius is 2. So now it's 2 times 2, which is 4. 4 times 90 degrees that's 360, right? So that would make just 1 pi, or just pi, right? So that radius would be 1 pi, or approximately 3.14. So instead, now let's say I change it to 3 for the radius. So then that's 3 times 2, which is 6. 6 times 9 is 54. So that would be, let's see, that would be 540 over 360 times pi, which then, let's see, what can go? I think 90 goes into all of those, so, or both of those. So 90 goes in here, oops, here 4 times, and 90 would go here. Maybe X goes in there bigger. Let's see, so hold on. 540 divided by 90 is, actually 180 goes into both of them. Goes into 362 times. It goes into 540 3 times. So that would give us 3/2 pi, or 1.5 pi. So 3/2 pi, or approximately, let's see, 4.71. So 4.71 for that one. Now let's change it up, make this 4 instead, see what happens. So now if our radius is 4, so that's 2 times 4, which is 8. 8 times 9 is 72, or 720, excuse me. So that's 720 over 360, and then times pi, which 720 divided by 360 is 2. So that's 2 pi. So this next one is 2 pi. So if you notice the pattern, what's happening is as we're adding one more unit on the radius, we're going up another 1/2 pi. And so that would be, 2 pi would be 6.28. And then finally 5, we put a 5 in here instead. It's going to change that and change our final answer. So if I plugged in 5 here, that's 2 times 5, which is 10. 10 times 90 is 900. So 900 divided by 360. 900 divided by 360 is 2.5, not surprising. Or 5/2 if you want to leave it as a fraction. Or 2.5, you could also do that. 2.5 pi. Again, it's going up by a 1/2 each time. So 2.5 pi. And that's approximately 7.85. And what they actually want us to do is take these values that we just found, these ordered pairs that match the radius with the arc length, and plot them here. And we're going to see if we notice some sort of pattern. So if I plotted the ordered pair right here, 1, 1.57, so over 1 and up 1.57, that would put me at about, there's over 1, over 1 and up about 1.5. Over 2, when I had radius of 2, it was 3.14. So that would be maybe right about there, just a little above the 3, maybe right here. That's not there. Right there. And then the next one was 3 and 4.7. So over 3 and 4.7 would be maybe right here. Maybe right there. And then the next one would be 4 and 6.28. And that would maybe put us right about there. And then 5, it's going to be at about 7.8 over 5 and up about 7.8, so close to 8. And I don't know, it looks to me almost like these lie on a line. Because I can see if I know if the radius was 0, if I had actually plugged in 0 as a radius, which doesn't really make sense, but if I had, I would have gotten 0. So just kind of thinking about connecting these, yeah, they definitely look like they lie on a line. So that's what I noticed. It looks like it's linear. Now the final thing we're going to look at in this lesson is converting to radian measure. So you've done lots of unit conversions. You've converted inches to feet. You've probably converted Celsius to Fahrenheit temperature. You've converted lots of things in science for sure. So, you could do like conversions of meters to yards, things like that. So as you discovered and explained too, which is what we just were looking at, the central angle is fixed at m degrees. The length of the arc cut off by a central angle is proportional. Okay, it's a proportional relationship. That's why that graph was a line, or varies directly with the radius. So in fact, you can see that the formula for arc length is a proportional relationship where m is fixed, when m is fixed, So when the measure of the angle wasn't changing, but you were just adding on one more unit to the radius, it was changing proportionally. So the constant of proportionality for the proportional relationship is m divided by 360 degrees times 2 pi. In other words, those are the things that are fixed every time. Whatever that m is, that doesn't change, and then the 2 and the pi don't change, because remember, pi is an actual number. It's 3.1415. So the constant of proportionality is defined to be radian measure of the angle. So if we took this, m divided by 360 degrees and times 2 pi, and we thought, well, let's see if we can just simplify that a little bit. Well, that 2 pi is really 2 pi over 1, right? And there's some things here we could do to reduce. Like we could reduce and cancel that 2 out of 2 one time, and out of the 360, 180, right? Because if there's something on the bottom that will cancel with something on the top, then we can reduce, right? So what's left on the top is m degrees and then times pi, and what's left on the bottom is 180 degrees. And in fact, this actually gives us a way of converting, no matter what your measure of your angle is, so we call that m, right, to radians by simply multiplying by pi divided by 180 degrees. So this is actually our unit conversion factor. If we want to find a measure of an angle in radians instead, we just simply multiply that measure in degrees by pi divided by 180 degrees. And then the degrees will cancel out, and what will be left is radians. So that's a unit conversion, just like we might use 1 foot over 12 inches to convert something to feet, or 12 inches over 1 foot to convert something that's in feet to inches, or whatever. This would be our unit conversion factor. So anytime we want to do a conversion, all we have to do is multiply our degrees by pi divided by 180 degrees. So for instance, if we wanted to convert 60 degrees to radian measure, and we just won't use this format, we'll just do this ourselves. We'll take our 60 degrees and we'll multiply by that conversion factor, which is pi over 180 degrees. So this is like the reduced version of this right here, of that conversion factor. So if I wanted to get this exact, I could think about 60 degrees as being 60 over 1. And I could think, is there something, when I multiply these together and I get 60 degrees times pi, well, actually the degrees are both going to cancel out, right? Over 180 degrees. Then I say, okay, what can I do to reduce this? Well, I know that 60 goes into 180 3 times. So I could divide that out of 180 3 times and out of 60 itself 1 time. And that would actually reduce this to pi over 3, or 1/3 pi, and again, radians. And we'll abbreviate that as rads. So that would be the radian equivalent to 60 degrees. Now let's say we wanted to go the reverse. So it says explain how to use the degree measure of an angle how to find the degree measure of one whose radian measure is pi over 4. So if I had pi over 4 and I wanted to convert it back to degrees, I could take this conversion factor that I used, pi divided by 180 degrees, and I would just simply flip it. Because anytime you have two things that are equivalent, you can write a conversion factor either with either thing as being the numerator. So like, for instance, when I was saying 1 foot over 12 inches, but you could also use 12 inches over 1 foot because they're equivalent to each other. So that's how a conversion factor works, is they're two equivalent things, and you use it in whichever way is appropriate for what you're trying to convert to. So if I were to take this conversion factor, 180 degrees, which is what I want is in degrees, over pi, and multiply it by pi over 4, right away what you'd see is that the pi's are going to cancel, right? And that leaves me with 180 degrees over 4, which is 180 degrees divided by 4. And 180 degrees divided by 4 is I'm pretty sure it's 45 degrees, and yep, it is. So that would be 45 degrees. Now this is going to be an important thing that we'll do down the road. In Algebra 2, we do a lot of unit conversions from degrees to radians. So it's nice that we're getting a little glimpse of it early here in geometry. So basically, you're going to use to go from degrees to radians. Maybe I should do this instead of using the degree symbol, because that kind of looks like a 0. We'll just say degrees. So if we want to go from degrees to radians, we use this conversion factor. We'll use degrees would be to radians. We want to put pi on the top and 180 degrees on the bottom, because that's what we want to cancel out as degrees, right? And then that's what we'll multiply by. And if instead we want to go from radians to degrees, we'll multiply by 180 degrees over pi. So here are our two unit conversion factors. It just depends on which direction you want to go. So again, if you're going degrees to radians, use this one. And if you're going to go radians to degrees, you're going to use this one. Let's practice a couple of these. So I want to convert 90 degrees into radians. So I'm going to use the one that has the degrees on the bottom because I want to get radians. So that's pi over 180 degrees. So that's really 90 pi over 180. And I can reduce 91, or divide 90 out of 90 one time and out of 180 two times. So that's pi over 2 radians. Okay. And then if I wanted to do 45 degrees, so I'll take that 45 degrees, rewrite that over here, and I'm going to multiply by pi over 180 degrees. Okay, so remember, pi is really like short for pi radians, right? We just kind of usually, sometimes that gets left off, but that's radians, right? And then if we wanted to cancel out our degrees, we'd have to have one that's on the top and one that's on the bottom, which is what we did, right? So that's how you know which of the two conversion factors you want. With whatever you want to convert to, that's what you're going to put on top. So we wanted to go to radians, so we put pi radians on the top. So that would give us 45 pi over 180 degrees. And I can reduce that 45 and 180. I could divide 45 into 180, and it goes in there 4 times, and it goes into itself 1 time. So that's going to leave me with pi over 4 radians. I don't think I left room for my units. I'll write it down here. Okay, so that's my answer there. So that's how you'll do a unit conversion from degrees to radians. And to wrap up, let's take a look at these questions. So you know that 360 degrees is the degree measure that corresponds to a full circle. What is the radian measure that corresponds to a full circle? Well, if I took this 360 degrees and I want to convert it to radians, right? I'll use the one that has pi on the top. Pi radians is really what this is, right? Over 180 degrees. So when I multiply, I end up with 360 pi over 180, because remember the degrees canceled out, so those are gone. So 180 can divide into 360, right? 2 times. So that would just give us 2 pi radians. That's going to be really important. We're going to learn this thing in Algebra 2 and beyond, called the unit circle. And the unit circle is measured as 360 degrees or 2 pi radians. And finally, what two pieces of information do you need to calculate arc length? So if we go back and we think about arc length, remember this was the formula. So we'd need to know, let's see, it was 2 pi r. We need to know these two things. We need to know this, which is the measure of the arc. Or alternatively, you could also know the central angle of the arc. And then you'd also need to know the radius of the circle that contains the arc, right? So if you know those two things, you can calculate arc length. And that pretty much does it for today's lesson. So thanks for coming to class.